السلام علیکم. سائنس کی دنیا کی طرف سے قدیر قریشی آپ کی خدمت میں حاضر ہے، اور میرے ساتھ حسان اور فصیح ملک بھی ہیں. اور آج ہم بہت خوش قسمت ہیں کہ ہمارے ساتھ فزکس کی دنیا کے ایک بہترین سائنسدان ڈاکٹر سچدیو میرے ساتھ موجود ہیں. ہم ان کے ساتھ بات چیت کریں گے، لیکن ہم ان کے ساتھ بات چیت انگریزی میں کریں گے. میں تھوڑا سا ان کا تعارف کرا دوں آپ کے ساتھ. ڈاکٹر صاحب ہارورڈ یونیورسٹی میں ہیں، تھیوریٹیکل فزسسٹ ہیں، اور ہرشل اسمتھ پروفیسرشپ ہولڈ کرتے ہیں. اور انہیں بہت سے انعامات مل چکے ہیں فزکس کی دنیا میں، جن میں لاسٹ آرسیگر پرائز ہے، آئی سی ٹی پی کا ڈراک ماڈل کا پرائز ہے، ڈراک میڈل ہے، اور اس کے علاوہ رائل سوسائٹی کے فورن ممبر ہیں، الیکٹڈ فورن ممبر ہیں، جو انہیں حال ہی میں دی گئی تھی. اور ان کا کام جو ہے زیادہ تر کنڈینسڈ میٹر فزکس میں ہے، زیادہ تر کوانٹم انٹینگل میں. اور اس کے علاوہ ایک جو بہت مشہور فزکس کا ماڈل ہے ایس وائی کے ماڈل، اس کی دریافت میں اور اس کی ایجاد میں ڈاکٹر صاحب کا بہت بڑا ہاتھ ہے. تو ڈاکٹر سچدیو، thank you very much for your kindness. You gave us this opportunity to talk with you. Can you please introduce yourself and also tell us about your family background a little bit?
ضرور. مسٹر قریشی، بہت شکریہ. مجھے بہت خوشی آپ سے بات کر رہا ہوں. اور میں انڈیا سے ہوں، پر میں ہندی تھوڑی عادت نہیں ہے، تو میں آپ سے انگلش میں بولوں گا، معاف
جی
کیجیے.
sure. جی
So I was yeah. So you want to know about my
yes
life
sir.
story? So
Yes sir.
yeah, I was
Yes sir.
born in Delhi,
Mhm.
and, and I grew up there. And but my parents in fact, my grandparents are all Punjabis. They all came from Lahore. Well before
Nice.
partition, they had moved to Delhi,
Mhm.
and so I have never been to Pakistan. Maybe someday, but in Delhi, yeah, I went to school and I spoke Hindi basically with everyone.
Mhm.
But then when I was about 10 years old, we moved to Bangalore, which is in South India, and finished my school there. And I joined the Indian Institute of Technology. I came back to Delhi. And at that point, my family moved to the US. My father got a job in the US. So I came to MIT, Massachusetts Institute of Technology here in Boston. And there I was always very interested in physics, even in India, to reading books and my classes and so on. But I started out as an engineer because that is what families want you to do.
Right. Right.
But after, well, I enjoyed it. My father was a satellite engineer himself. And but in MIT, I ended up working in Professor Kleppner's laboratory in physics, and I really enjoyed that work. And so I've been a physicist since then. I also had the good fortune to have a postdoctoral fellowship at Bell Labs. So Bell Labs is a very famous laboratory where the transistor and the laser and many other fundamental things were invented. But it doesn't really exist at the same level anymore. And after my postdoc, I was a junior professor at Yale for some time, and now I'm at Harvard. Yeah, okay, so that's a quick, and when I first switched to physics, there was, some hesitation, but in the end, my family also was fine. They said, go ahead, try it. And fortunately, I think I was lucky to be at the right place at the right time, and I've made some contributions that are now well known. So,
Right.
and yeah.
So was Harvard your choice, or do you think that was just being right place at the right time?
My choice, you mean to coming here as a professor?
Yes sir. Yes.
Well, I was here as a PhD student also,
I see. Okay.
before I went to Bell Labs.
Yeah.
And then I was a junior professor at Yale, and no, I was perfectly happy at Yale, but of course Harvard has a very strong department in physics, and
Right.
So they called me and offered me a position, and it's hard to say no to that. I wasn't looking at that time, but I guess some of my work had come to their notice, and then they
So,
offered
okay,
me a position. So I was very happy to come, of course.
right. So let me ask you sort of a generic question, then I
Yeah.
think Hassan will take over, and then Fasi. So can you tell us a little bit about what you are working on these days? What are your current research interests?
Yeah, so these days I work largely on superconductivity. So this is a
Okay,
phenomenon where in certain materials, when you cool them, then the electrons can conduct
right,
electricity without any resistance in principle. Uh,
right.
and this is very useful for many possible applications, especially those that require high magnetic fields. So like the MRI machines that you see in many hospitals now use superconductors. But my interest is really on the basic physics of what
Right.
makes a certain material a good superconductor. And this involves, applying the tools of quantum mechanics. Quantum mechanics is the version of Newton's laws that applies to microscopic particles like the electron.
Right.
And so it's really a question of understanding the quantum mechanics of many, many electrons. But while you're doing this, the methods you use are the methods of quantum mechanics and also what's called quantum field theory.
Right.
And in fact, many of the methods that Professor Salam used for the theory of weak interactions, the so-called gauge theories, they're also very important in my work. So, so in the end, I'm doing some combination of quantum field theory, but applying it to real materials in the lab. Yeah.
So just one question, you mentioned superconductivity. So there was a lot of hoopla last year, I think, about low temperature superconductivity. Do you think there's just bluff, or there was something to that?
There is something to that, but the hoopla was about some really strong claims about room temperature superconductivity, and that issue, if everyone was skeptical, but and I don't think it's informally settled yet, but at this point, it's pretty clear that there was some misconduct there, and that's not real. But that shouldn't, and unfortunately, that is the time everybody hears about the field, about superconductivity, when it's a bit unfortunate that the time they're hearing about it is not the right, may end up being some sort of fraud, although it's not been fully settled yet. But the underlying it is a very basic and important phenomenon, and there was some interesting discovery in Germany about raising the temperature for superconductivity in certain materials under high pressure. And that, I think, let's see, people are testing it and it looks pretty plausible. But, the big advance in superconductivity, which is related to what I work on, is really the so-called copper oxide superconductors. They were discovered in 1987. By Bednorz and Mueller, and they got the Nobel Prize for that a few years later. And that's still the very best superconductor we know that can superconduct when you put it in liquid nitrogen, which is not that hard to obtain.
Right.
And that's absolutely a settled phenomenon. No question, it's correct. And those materials are the ones people are using, and the ones I think about. So the recent developments are more of a distraction so far, but the field goes along and it still has very basic questions that we're thinking about.
So you mentioned before that you did your engineering before coming to physics. So I want to ask that what developed your interest in physics? Was it there before you started your engineering, or was it developed after you had finished your engineering?
It was already there from the very beginning, in high school, in school, we had physics classes. I mean, we had good teachers. I was at St. Joseph's Boys High School in Bangalore. It was an excellent school. and we even had a good physics lab. And I also remember reading some books by Feynman. The Feynman lectures were available, and really fascinated by quantum mechanics and things like that from a young age. Yeah, so, and I started out in electrical engineering. I said, yeah, okay, maybe we'll have some basic physics here too. But then after coming to MIT and really, seeing firsthand all the exciting problems that many of the professors were looking at in physics, yeah, I wanted to at least try to be part of that world. Yeah.
Right. So I have one follow-up question. So
Yeah.
You said that you read a lot of books from Feynman. So was your initial interest to go into particle physics, or did you want to go to condensed matter physics from the very start?
Yeah, that came much later. So when I came to graduate school, I wasn't sure. I mean, particle physics certainly, in the time of Abdul Salam and others, was definitely the exciting field where there was some remarkable progress in a very short time. But by the time I started in my PhD, what's now called the standard model of particle physics, which describes, quarks inside a photon and electrons and basically every particle that we know, was pretty much in there. So, and it seemed like the problems that we're addressing were, first of all, not only very difficult, but also disconnected from experiments that would be done, over some reasonable time frame. On the other hand, in condensed matter, I saw that there were, again, a lot of exciting developments happening, like the discovery of the high temperature superconductors happened when I was very young, just starting my career. And it seemed also that the questions we were asking were equally deep. They really probe the very nature of our universe by thinking about what happens to electrons in when lots of them get put together in certain materials. And yeah. So just that combination of fundamental and deep questions, along with possibility of almost daily contact with people working in the lab with experimentalists, that convinced me to choose condensed matter physics. Yeah.
Fasi, you're mute.
Sorry, I can't hear you.
Yeah, sorry, I had muted myself. Yeah, so you said that when you were in school, you had some very good teachers. Of course, teachers have a very good impression on shaping the future of young students. And then I believe you also taught a course during pandemic in India with the collaboration of ICTP. So my question is regarding your experience and like how was your experience as a teacher compared to your own teachers, and what in general teachers can do like to like teach the students in such a way which could like help them decide their future or like figure out what their interests are, like where they want to go. Do you have some insights on that?
Well, yeah, that's a very good question. I've been teaching for, I don't know, 35 years now, so I guess I have a lot of experience. And yeah, there's no question that, having a good teacher can completely make or break a student's interest in certain areas. And, the teacher doesn't have to be completely knowledgeable, but they have to be, I think, in the end, passionate about what they're doing. You have to convey the love of the subject and the love of the field. And if you do that, then the students interact and they ask lots of questions. And if you don't know the answer, I just say, I don't know, go look it up, or go find out and tell me. I think that can often be very effective. And the students, I try to inculcate, self-study, that you should, okay, all right, here's a good question that you've asked, and I don't know the answer, but why don't you look into it and come back and talk about it next time or something like that. And so so that I think helps students get some self-confidence when they, first of all, they see me hesitate. And I'm not acting, I'm really saying, I don't know. I think that's good for students to see. And, they see that I also had to start from nothing, and I slowly learned things, and now with the benefit of experience, I know a few things. So there's no reason why they shouldn't be able to do it themselves. I mean, I should say now, also the situation in India now has improved dramatically from my time.
Right.
Now there's many institutions with very good physics departments and also great experimental facilities, and it's really come a long way. And now, of course, with the internet, like you said, the course that I taught during the pandemic was actually not ICTP. It was at the IAS, the Institute for Advanced Study in Princeton. So I was supposed to go to India for a few months to teach a course, but the pandemic, of course, made that impossible. So I taught it online, and actually that turned out really well because the facility was good enough that students in India were actually asking questions while I was lecturing in Princeton. And now those lectures are online, they're on YouTube, and I'm finding many people are watching them. So it's reaching a much wider audience than initially. Yeah.
So Dr. Sachdev, you mentioned previously about, in 60s and 70s, there was a lot of work on particle physics, and you mentioned Dr. Abdul Salam.
Yeah.
What's your opinion of Dr. Abdul Salam's contribution to basic physics, theoretical physics?
Well, he's one of the great physicists of the century. So the work that he won the Nobel Prize for was, putting in certain key ingredients of what we now call the standard model of particle physics. So understanding, how the, electrons and neutrinos and radioactive decay, how they all come together and explain the spectrum of the certain sector of the standard model. So, that was really, really important, of course. But he also made a number of other contributions. He set up the basic formalism of what we call supersymmetry, and many fundamental things on structure of quantum field theory. And then, of course, beyond that, he worked very hard to set up the ICTP in Trieste, and that's had an enormous influence, certainly in India, and I expect many Indian scientists come there a lot, and from all over the world. I think Pakistan also. Yeah. So that was, he put a lot of effort into that, and that's and I think that was a really exemplary service to the physics community and to the world at large. Yeah. I actually, last summer, I had the good fortune to meet his son, Mr. Ahmad Salam, and he invited me to his house in London. And his original study, Professor Salam's original study, is still there with all his papers. Wow. And Ahmad was showing me his letters and how he used to sit on the chair and work out equations. And a lot of his scratch work was there. So I could see that he also struggled. But of course, eventually, good things came out of it.
So have you had a chance to actually interact with him?
I wouldn't. So when I was very young, as a young student, I went to ICTP, and there was a big conference with lots of people. And I remember there was, at lunch, I was sitting at a table, and he came by to say hello to everybody. So I may have even shaken his hand. I don't know. That was about it. I was, I was just a student. I'm sure he didn't remember meeting me.
Sure.
But I think that was the only time but I did see him and interact with him very briefly once. Yeah.
Dr. Sachdev, I have the question regarding your own, you have done a lot of work in the past 3-4 decades, but there's one which everyone knows about the SYK model.
Yeah.
I read that I have heard you saying that you started that as a toy model back in 1990s. And so my question is regarding that, like, what are these toy models? I'm asking these questions for the young students, especially like undergraduate students in
Yeah.
Pakistan, because they do not really understand like what's the advantage of these toy models if you cannot immediately realize them. So my question is, what are these toy models, and how do they help us understand the actual realization in materials?
Yeah, those are all great questions. uh, well, toy models, we are asking to begin with some conceptual questions. So I was puzzled by a lot of the phenomena in the copper oxide superconductors. And, we know something about the microscopic structure of those materials. We know there are electrons and exactly which atoms they're hopping on. So we can write down what you call a realistic model. That is or you can write down some Schrodinger's equation, which describes the quantum mechanics of all these electrons. So in principle, the equations that determine the fate of those electrons are completely known. But that doesn't mean you've solved the problem, because nobody can solve those equations. They're just too complicated. In the end, those equations predict certain phenomena, and what are the phenomena we'd like to know. Okay. I mean, the same is true even in particle physics. I mean, the standard model, you write down everything. So people solve various simpler models where you can solve them, but then you get some conceptual understanding of what the phenomena are. I mean, and that also happened in Professor Salam's work, where the theory of weak interactions was, there are a number of simpler models that people had, and he looked at before you come up with the final answer. So in my case, what had become clear, not just to me, but to many other people, was that what we really need to understand something better was the nature of what you'd call many particle entanglement. So entanglement is a strange feature of quantum mechanics, which Einstein called spooky action at a distance. And Einstein himself was presenting it as a toy model of two electrons. So you imagine you have two electrons, like there are two electrons in a hydrogen molecule, and you're able to separate them without disturbing how they're spinning on their own axes. And if you could do that, it seemed to predict some very complicated, unnatural effects, where if you observe the spin of one electron, it would influence the spin of the other electron instantaneously, even though they're really far apart. All right, so that's the basic. That does happen, and it's been tested in various experiments, realistic experiments since then. And that's the basic structure of quantum mechanics, the nature of quantum entanglement. So that was two electrons. And what we wanted to understand was what happens when you have 10 to the power 23 electrons. What can they do when they start entangling with each other? Well, they can do a lot of things, we now know. In fact, we probably only know a small part of what they can do, depending on the conditions they're in. There's many, many possibilities, and we've only begun to classify them. So the SYK model, or at the time it was only S and Y. Y was my student, Jinwoo was a model where we said, okay, let's take a simpler model where instead of putting the electrons on a square lattice, which is what happens in the copper oxide superconductors, you put them on a cluster where they all interact with each other. So initially that seemed like you're making the problem even more complicated, because they all can interact with every electron can interact with every other. But there's some analog of what's called the central limits theorem in statistics. There's a similar analog in quantum mechanics. It turns out that in this limit of the SY model, you could actually figure out. So you could realize a state of matter in which there's complex entanglement among all the electrons. And this state had many, many similarities to things that were being observed in the cuprates. So I was very excited and, thought this would get everybody excited. This is 1993. But like you said, it's a toy model. It's not really what, and people were skeptical. I said, how can this, the model, yeah, that's nice, but it's a very artificial model. Don't bother me about it. That was the reaction of most people, almost all people. But not everyone. There was my friend from Paris, Antoine George, was very interested, and we started working on it. And so, eventually, now 25, 30 years later, we made a lot of people got interested when Kitaev, the K of SYK, entered the. So he simplified the model so that you could do even more things with it. But before that, I had pointed out in 2010 that this toy model that it seemed like it was a model of a superconductor could also be a model of a black hole. And that proposal was also met with a lot of silence for 5 years. Anyway, but now, everybody seems to accept this, and it's had a lot of influence. So, of course, I'm very happy. And part of the reason now it's become more accepted is now we know how to go from the toy model to a realistic model. It's all, now we can actually, now we've learned so much from the toy model that we now can take a realistic model where we actually have a square lattice, we have, all the microscopic physics that we know is present for the superconductors, and then compute with the benefit of our experience in the toy model some properties that you can compare with experiments. But that's very much ongoing work, and we made a lot of progress in the last few years. And similarly, on the black hole side too, it's gone from being just a toy model to a much more realistic model of certain types of black holes.
I have a follow-up question regarding the same one. I guess I read it or heard you somewhere saying that when you were thinking about this problem, you had some issues, but you finally got those ideas from your string theory friends, uh, like regarding mathematics or like some other intuitive ideas regarding this model. Can you please share some light on that?
Well, there's obviously a lot of interplay. So, I was thinking of the model as just a model of, certainly in 93, I didn't even know what a black hole was. I was thinking entirely about superconductors. But by 2007 and so on, they started to be a general emergence, and I wrote some papers on it, how there's some deep connections between entanglement of electrons in superconductors and entanglement at black hole horizons. This is a very broad connection, which a lot of people were developing. And then I heard from my string theory friends about a certain type of black hole. I didn't know much about black holes. They were describing the quantum properties of a certain type of black hole. And as I'm listening to them, all the properties they were listing were properties I knew from the SYK model, from the SY model. It wasn't even, K had not yet entered the fray. And so that was kind of a big eureka moment for me. Okay, it's not, the SY model, it was really more of a toy model for superconductors, but it was much more realistic for black holes. And that is what I learned when I learned the physics of black holes from my string theory friends. So I wrote a little paper pointing all this out, that, this is, it's all well and good to have a very general connection, but here's a very specific connection. You can even match numbers from the SYK to black holes. There's a specific connection. And that's now, really become much more precise also, thanks to the fundamental contribution by Kitaev in 2015.
So it means so like for the young students, they can get this lesson from this history, your history, that even though they are like doing research in certain field of physics, they should have some knowledge of like what's going on overall in like all other fields of research areas of physics. Because sometimes, as you said, in your case, it helps just to relate ideas like similar kind of things that are going on in other fields.
Yeah, no, I completely agree with that. I mean, one should be a scientist and or and really be interested in everything about that's going on, at least at some level. But these days, a lot of exciting advances are happening in machine learning and AI, and I'm trying to learn those. Perhaps they'll have some impact on physics too. We'll see. Yeah.
Dr. Sachdev, do you have any opinion on what do you think is dark matter and whether there's any hope that in the next few years or maybe in a decade, we will break that mystery?
Yeah, I wouldn't say I have a very knowledgeable opinion because I don't work on that area, but but I should have some knowledge. Right? I just said so myself. Yeah, I mean, I think the evidence that there is dark matter out there is very strong. That there is definitely, some large fraction of the mass of the universe is in some matter that we have not seen in any of the the optical or any other frequency spectrum. And there are many experiments out there, many people who have spent their lives trying to detect it, and there's many going on. And there are many possible candidates, essentially all of them involve some extension to the standard model of particle physics.
Right.
And which of them is going to be the right one? Yeah, that I'm going to have to say. But my sense is from from various talks I hear that people think we're getting close. I mean, the list of candidates is now reduced, and hope maybe in the next decade or so there will finally be some clear-cut identification of what particle is it, or maybe more than one, that's causing these effects. Yeah, I mean, so dark matter, I think, is it's a very solid field of research. I mean, a very well-established field of research, and I think that's based upon some very sound reasoning that there has to be. A little more spectacle is what you call dark energy, having to do with the cosmological constant and the rate of expansion of the universe.
Right.
That the data keeps changing and people have very radically different opinions. Who knows what? But dark matter, I think, it's something we see from nearby galaxies. We don't have to talk about the whole universe. And it's the evidence from gravitational lensing, for example, is really very clear that there's dark matter out there.
Right.
Yeah.
Dr. Sachdev, I have a question regarding it's like a kind of comparison. You said that the Indian education system has changed a lot since like you were a kid studying there, and now when you start a course 2 years ago, 3 years ago there, like it has improved a lot. There's a huge difference between back then and now. But the situation, like if you look at Pakistan, I'm not sure if you follow these trends, but our education system is still not like as good as the India's is. Like we still have a lot of students coming here in European or America for PhD, but not as much as in India. And even those students who are studying in India in institutes like IITs, uh, they are still like performing very well, writing well researched papers. So the question is, what do you think like countries in that region like Pakistan, Bangladesh, or like the neighboring countries compared to India, what they should do so that at least they could be able to lift their education system as good as the India's is at the moment? Like not talking about the European or the American systems, but we see a huge difference between India and the neighboring countries. So, do you have any insight on it, like what possibly could be done?
Well, this is not, I mean, I can only talk about my own experience. It's hard for me to, I mean, so first of all, I was referring to college level and above. I mean, school, still this, I mean, I think there's certainly a big push to expand primary education to everybody, and I think Pakistan and Bangladesh have done equally well on that. But at the university level, you know, I think starting from Nehru, there was a huge investment in setting up the IITs and many other institutions. And now, you know, now there's 25 IITs or something, or 20, something like that, and many other Institute of Sciences, and they've all grown. And I think the key was to, first of all, government investment a lot. And, you know, at the time, and it took some time for it to pay off. So there were few people had the vision that, okay, this is what needs to be done, and it'll take 20, 30 years, but eventually it'll start paying off. And I think that is what has happened. So the investment, and then, you know, I think also important is a lot of autonomy. Government invests in them, but then you give the scientists the power to run the place, and you know, and have an open and fair system for selecting the students and the faculty. I mean, there are a lot of universities, also older universities in India, which didn't fare as well, but now they're coming back. But a lot of them, you know, okay, I don't want to name names, but you know, my father went to a university, which is a very old university, had a very good science department, but then it, you know, became a lot of nepotism, people hiring their own students, and it just became nothing. But I think a lot of that is starting to stop now, and there's, you know, emphasis on excellence and freedom and independence. I think these are very important things that institutions have to have.
Yeah, actually, yeah, I believe this gives answer to my question. I mean, we don't directly need to name names, but yeah, that like nepotism and hiring the people, you know, and having no autonomy to the people who are actually running the institutions and doing real science. Yeah, these are actually the factors. Thank you.
Yeah, no, and no, I'm not saying India is perfect. There are a lot of institutions that had problems, but there were a few that didn't, and now they've excelled. And then this culture, once you get a few that are succeeding, then that culture spreads to other places also. It becomes much more widespread. And fortunately, that has happened in India now. I mean, what I now find remarkable is something I couldn't dream of when I was a student in India. You know, many of the graduate students, you know, they travel to conferences abroad. Almost all of them have at least been to one conference during their career. So they're exposed to or they come to ICTP. And so being exposed to the culture of science all over the world is also very important. And I think that was also, you know, Abdul Salam's vision in setting up ICTP, that just having exposure to science in general is really, really important for just an overall culture of the society.
Right. So, Dr. You know, there are people like you who are, you know, sort of, you know, from day one, they are interested in physics and all that. But a lot of kids who are actually smart, otherwise intelligent and capable, somehow they have fear of mathematics. And there is this notion that, you know, if you have to study physics, you have to do a lot of math, and, you know, some people get turned off. So do you have some ideas about how we can help, you know, educate kids about, you know, why math is important? I mean, we get this question a lot of times, you know, where we'll use math in real life, right? And why this math is being taught. Do you have some suggestions on how we can allay that fear?
Well, I mean, when I myself, when I don't know that much math, relatively speaking. So if I take a pure math course,
Mhm.
it can seem very dry and really a bit pointless. So I would say that you have to see math in action. I mean, and that's how you learn it,
Yes.
So
Right.
you learn, if you're learning calculus or integration or differential equations, and well, if you're applying it to some physics problem and you see how it works and how you need it to understand some experiment or some physical phenomena, then it becomes like the language. It's mathematics is just a language we use, and I've certainly the most advanced mathematics I've learned is while I'm doing the physics. You
Mhm.
learn the math as you're doing, or you're doing statistics, or you're doing economics. You learn it while you're doing some application, is what I would say. That's probably so one shouldn't make it some sort of abstract set of rules that people came up with. And that, and also, at least from our part of the world, it's worth emphasizing that many of the key things in mathematics came from, from our part of the world. The whole number system and algebra,
Yes.
and they all have origins in India or the Middle East. And
Yes. Yeah. That's a very good point, that maybe we need to excite kids that way, that this is our own heritage. This is not something that was invented in the West.
Yeah. The Romans were doing, if you try to do math, what we're doing in math today using Roman numerals, nothing will happen.
Yes, exactly. Right. It's hard to imagine
And
the value
even certain
in
aspects
modern.
of calculus were
Yes.
invented in South Asia, and but not, of course, then there was a huge explosion in 16th, 17th century in Europe, which our part of the world got way left behind, and now have to catch up.
Yes.
So I have a question about your experience of writing textbooks. So I mean, you have written a number of books, which includes this book on quantum phase transitions in the late 90s, and this on holographic quantum matter in the late 2010s. So a lot of people who have written textbooks, they say that before writing the textbook, they think that this textbook probably will be over in 1 or 2 years, but when it actually happens, it takes much more time than that. So did it happen with you? And were there some other, experiences that you had while writing these textbooks that you want to share?
Yeah, well, I think writing the first draft, if first of all, you have to think, what do you want to say? And you have some message you want to convey in some broad sense. And in both cases, and in fact, I have a third book now, is all based on courses that I taught over the years. So I've probably had been teaching this course at least 4 or 5 times and developed notes. And then I said, okay, after 5 I said, now it's time to put it all together. And then writing the first draft is actually quite easy because you're just getting everything done and you know what to say. And then, it takes 6 months to, if you write even 3 or 4 pages a day, in 6 months you have, 500 pages. So it can be done if you do it steadily, which you do. But then comes the hard part. You have the first draft, and now you have to check everything, and you have to put in all the references, and you have to reread it and rewrite it. Yeah, that can take a year or 2. Yeah, but the key in my case, of course, has been to first get the ideas organized by teaching a course. And you often find okay, I'm going to present it this way, and then first time you do it, then the students, you just get a lot of blank stares, and you realize, okay, this is not going to work. Let me reorder things and try to do it again, or teach it in a different way. And so, at least with the first and the third book, I went through that iteration over 4 or 5 years, maybe more.
I see. I've heard from some authors that they say that probably one of the most boring parts of writing a textbook is to set up the index. Is that true?
Yes. I mean,
Okay.
nowadays it's not so difficult because you have some electronic tools. I can imagine if you didn't have these tools, it's really terrible. But now it takes a few days of work. You just have to go in and every page put in a little notation. Then the software will do it automatically after that.
I see. I see.
Yeah. But, just checking everything, getting all the figures, writing the problems. Yeah, that's boring, and it takes a couple of years.
I have a question again. Again, it's related to the education and young students, especially students who are doing undergrads in physics. And the question is related to problem solving in physics, and I would like to have your insight on that, like your thoughts on that. We have, like specifically in Pakistan, almost like non-existent culture of problem solving. Like even the teacher, they probably ask you the questions which they teach you as theory in class, and they will like give you those questions which you just need to write down. They will not ask problem. There are some institutions which do make
Yeah.
students solve problems, ask problems in exams, give homeworks, but like majority of institutes, they do not put student or they do not train them in problem solving. And the result is by the time students get their degrees, they have physics degree and they don't know how to solve problems. So I want to ask you to give some thoughts on like how important it is to solve problems like the chapter ending problem in books and how they are helpful in research in general when you enter your grad school, a PhD, how these techniques of like solving problems help you.
Yeah, no, you're absolutely right. I mean, problem solving is key. And, yeah, education, and even, I mean, it was also the case in India. In my education, quite a bit of the education was just memorizing on all kinds of things. And then that's not good, definitely. But there were always a few teachers who would talk to you and give interesting problems to work out. So I think that definitely is an important responsibility of teachers to make sure that you're not just giving a bunch of facts that they have to memorize, but maybe give a little bit of the history of the subject and how these facts were discovered by somebody asking a question and being very confused, and then making a guess, and somehow and we only hear about the correct answers, right? So but one shouldn't be afraid to venture into a different arena, and all of that ability to be curious and to ask lots of questions. You need a lot of experience with, start simple with lots of problems, and yeah, but it's a very hard task for a teacher. It takes a lot of work, and so teachers should be better compensated, no question, to come up with good problems that will interest the students, which they will enjoy, rather than seeing it as some annoying work they have to do.
I mean, let me do a follow-up question on that.
Yeah.
So, I mean, when you are in undergrad, the kind of problems that you have to solve may take probably at most a day to solve. I mean, there may be some exceptions, but most of the time you can solve them in a day at most. But when you come to graduate school, a lot of problems may take more than a day. I mean, it may take weeks for you to come up with a solution. And then when you're doing research, the problems may take months or even years to solve. So the thing is that for everyone, it's not easy to do this transition, because if suppose that if there is a person who has this habit of solving a problem in a day, and that person now has to solve a problem that may take a year, that person may think that, okay, probably I'm not good enough to solve the problem, but it's not necessarily true. It may happen that the problem is hard. So how do you think that students should adapt themselves for this transition to go from undergraduate level problems to research problems?
Yeah, no, those are great questions. I don't know if I have very good answers. I think one strategy is, first of all, you can break it up, break it up. You got some very difficult problem. I say, okay, can I ask a much simpler question? And then make a little progress on that question. So if you have a series of small steps where you think you're moving along, you're not just stuck and staring at the window, then it's very frustrating. But if you can find, simpler or smaller cases that you can look at, then and keep making progress, and then you can keep going at it. But often, sometimes I suggest problems to my students, and then sometimes they just disappear, and then I have to call them up and say, what's going on? Well, it's too hard. Well, okay, if it's too, and then I say, well, why don't you come tell me? Or sometimes, the problem itself is wrong. I mean, it's not as if there's a God-given problem that you have to solve. So, a student could say, okay, this is looking really hard, and then say, okay, I think this is the wrong question to ask. Maybe there's another question to ask that could help you make progress. So you have to treat the questions or the problem as not something, precisely the things that you have to solve. You have to maybe ask a different question, or ask a simpler question, and keep making steps. And sometimes you come up with a problem and you say, okay, at this point, I don't think I can solve this. Fine. It's not as if you wasted your time. You put it aside. This has happened to me several times. I just, okay, this is fine. I'm going to close this notebook. I just don't know what to do next. I put it aside and kind of forget about it for a while and do something else. But then a little, year later, I'm thinking about something, and then I remember, oh yes, this can apply to that problem that I was looking at a year ago. Then you bring back that. So you're, struggling with a problem, but it didn't seem like you didn't make any progress. It's not entirely wasted time. You have to realize, okay, you looked at a lot of dead ends, and that's very useful knowledge that maybe someday will still be useful to you. You don't know yet, but it will be useful later. So that's been my experience. So I think that gives you, you don't get frustrated and just give up. I mean, it's the nature of but it's, it's satisfying eventually. Maybe you have to wait a while, but it's well worth the satisfaction later on when suddenly something, make progress, and you see something in a new light that nobody else has seen. And it's not always, I'm sure that was the case with Professor Salam too, that it's not that he sat down one day and said, this is the theory. It just doesn't work that way.
Right.
I'm sure there were many dead ends. And then, and what's also often happened, I work something out, it looks like I haven't solved anything, and I write a little paper on it, and I say, okay, fine, enough to get published, and that's the end of story. But later on, you find, oh, well, actually, that idea has other applications. It's got, so, yeah. So just being more flexible, asking different questions, and recognizing that the biggest difficulty may be not finding the solution to the problem, but that the problem is asking the wrong question.
Right. So you mentioned that.
Yeah,
so
sorry, go ahead.
I have a follow-up. So you mentioned that it can happen that you may come to a dead end, and then you get some other idea, and then you have this aha moment where you realize that you can apply this idea to the problem that you were solving before. But to have such moments, you need to have a lot of dead ends in mind, right? So it means that if you have a dead end, it's not necessarily a bad thing, right?
Yes, absolutely. That's exactly what I was trying to say. I mean, of course, easy for me to say all this when I have a tenured position. When you're a young person, right, you have a limited time horizon. So all I can say is, I am actually very happy when my students come back to me and say, the problem you gave me didn't make any sense. I think you're giving me the wrong problem, or I didn't do my job to think through exactly what the right question was. And often that is the case. I'm very happy that the student told me that, okay, let's try to reconfigure this. What's the worst thing? A student can just disappear for a year and then come back and say, sorry, I've made no progress. And then Okay. And it could be because of my fault, because I didn't give the right question. So don't hesitate to question your advisors.
Dr. Dev, these days seems to me that the attention span of younger people is shrinking because of social media and all the other things.
Yeah.
And also, there's a lot of now propaganda against science and technology, which, I see that in India and Pakistan, I mean, here in US also, but in Pakistan, at least I can tell you, it's a lot more pervasive.
I mean,
What do
in
you
what
think we
sense?
can
You
do?
mean
Yes.
because it causes climate change and all of that, or nuclear war, or things like that?
Yes, and also in general, in Pakistan especially, there is, traditional thinking, right? There's, conservatives who, who don't like change, and technology brings change, so they seem to be, reluctant to accept that. But my question really is, what do you think we need to do to encourage younger people to take more interest in science and technology and see that that's where the future is?
Yeah, I don't know. That's a good question. That's a good question. I don't have a good answer. Well, I mean, at least like speaking from what I see in American schools, there's an incredible discussion of all the bad things that are somehow due to science, like
Mhm.
pollution and this and that. But
Right.
maybe they can be a bit more, certainly I think a lot more emphasis on, well, many of the things we take for granted, that including, starting with the iPhone, that's the
Right.
example I often give. Let's take your iPhone. Almost everything inside it is due to science and physics and research
Mhm.
that's not that
Yep.
long ago.
Right.
This could not have existed even 15 years ago. And that's certainly something every young person values. So they can't do without that. Yeah, I would say I mean, speaking a lot more about how basic scientific knowledge is the key, not just to technology and many technological achievements that you take for granted, but also for, just understanding our place in the universe, and for,
Mhm.
as a universal human quest. I mean, it's something that humans have been doing since the very beginning.
Right.
Starting with tracking the planets and so on. We just want to know our place in the universe, and science is a big part of it. And so, I mean, you could also view religion as something like that, but what I often say is that the reality is much more fantastic than any religion. When we look at the size of the universe, how big it is, or how many black holes are in it, and
Right.
that is far more fantastic and bigger than any imagined in any legend in any history that you may find. So I guess inculcating that sense of fascination in part of this universal human quest is something we should do, and that'll get young people to respond to that.
So I have a question about popularizing science. So as you surely know that a lot of ideas in the modern theoretical physics have become very abstract. So because of this thing, popularizing those ideas is becoming difficult to the layperson. So do you have any suggestions that how these very abstract ideas can be, popularized to the, popular audience?
Yeah, I mean, I agree that often many of the popular science discussions get very abstract, and I agree they shouldn't be. Somehow they present science as some very abstract thing, and then there's some black magic, and then it all seems to present it as something that mere mortals couldn't understand. And I think that's wrong. It shouldn't be presented that way at all. Everybody can understand it if they have, I mean, if presented the right way, and if they spend more than 10 minutes talking about it. It has to be, you need, okay, half an hour to explain some scientific concept or anything. Almost anything can be explained to anyone, at least the basic outlines. But it requires, as you said, some attention, some care. So I've given, numerous public lectures, and I gave a lot of thought to how to present like quantum entanglement. And I always try to do it by relating it to experimental phenomena, to observations of various types. There's Carl Sagan was a very good science popularizer. And you always to put it in context of observations, astronomical observations usually. And I think there's no reason the same can't be done for modern physics. And I think there are people who do it well, but there are also others who make it seem more abstract than it needs to be. There's certain directions like string theory that are very abstract and difficult to explain. But it's possible to do it by focusing on, some of the physical consequences of string theory. And there are people who do that well. But I can invite the audience to, just Google, go to my YouTube channel. There's a few public lectures, and I'm trying to present some recent ideas and frontiers of research to a general audience. And I don't know how well I've done it, but sure. Okay. But it definitely requires some effort from the people presenting the talk.
I have a question, and it's guidance from you for young students, especially in like the South Asian, the Pakistan, India, and Bangladesh, these countries, the students, how who want to do PhD in sciences, specifically physics. What should they do, like to build their background that makes their basics of their respective subjects strong, and what they should be focused on if they want to be good researcher?
Well, certainly in school or, just the basics, there's no alternative to, learning basic mathematics, a little bit of, you don't have to go to very high-powered mathematics, but the basics of calculus, the basics of linear algebra, certainly everyone should know, even if you're not sure exactly what field of science you're going to go into. And similarly with physics and chemistry and biology, I think I don't think one needs to really start jumping into some, like some genius into string theory right when you're 15 years old. Often that's not the wrong thing to do. I think more important is to learn the basic facts well and not just memorize them, but really understand why we accept these basic facts. Well, they're not something that somebody wrote down and we had to obey them. They are facts based upon a lot of trial and error, a lot of experiments, and a lot of wrong turns that led to these structure that we explained to you. So if you start appreciating that and understand where it came from, I think then you'll be ready to do whatever you want later on in life.
Yeah, thank you very much actually for this comment. I just want to thank because since I told you we have like 800,000 of like people in our group who almost all the time, ask us the questions about black holes, string theory, and these kind of like higher dimensions, these kind of questions. And we always try to tell them that you first need to know the basics. I mean, Hassan sitting here, he is doing research in string theory. I'm doing condensed matter theory, but we always try to tell them that you don't need to jump to like string theory when you're in high school. What you really need to know is like Newtonian mechanics, maybe those are the basics, and then you build your base. So thank you very much. Actually, think that because this will hopefully help us like make those young students realize that what is the right path. Thank you.
Yeah, I mean,
I've
most
seen.
important is to enjoy what you're doing and develop a passion for it. And it could be many different things in science or maybe other related fields. And as long as you have the passion and the interest, then other things will happen, I think.
I just want to say that I've seen students who want to study something like ADS-CFT, but they
Yeah.
can't even solve a differential equation. So even if I am working in string theory, I would not recommend this path, because there is no use of learning ADS-CFT or string theory or quantum mechanics even if you can't solve a differential equation. I mean, you
Yeah,
have
well,
to
but at the same
have good
time,
foundation.
I also, I have students, but I try to at least explain them the basic idea, and I say, all right, this is what I don't, I try not to dismiss them and say, but okay, that's a great interest. I can tell you a little bit about it, but now let's go back to some other things that you should learn before coming here.
Right.
I mean, the general idea one can convey in some pictures, but of course that doesn't mean they can actually compute anything. That takes years of work.
Right. Exactly.
So, Dr. Dev, anything that you may want to say to our audience that we have not discussed yet?
Oh, okay. So I'm, very happy to talk to you all and keep up the interest in science. And I hope, it's really, I would say, it's really very special privilege to be part of a worldwide scientific community. It just makes you part of some common human effort, and I encourage you all to be part of it.
All right, Dr. Dev, thank you very much. It's a great honor for us to have this opportunity to talk with you. So thank you very much. You have a good day.
Thank you for your interest.
Thank you.
All right, bye.